We're now going to take a look at the big picture of using these high-level languages, writing these programs, and this is going to be what we call software engineering. Now, most students will think that the big part of designing software is all about writing the code. It's all about understanding the syntax, how to declare variables, how to write statements, the proper punctuation, and there's always these compile errors if you don't follow the syntax rules or all these bugs with the program. But most students will think that the bulk of the effort of the software development process is devoted to the implementation, taking the algorithm, turning it into code. But that's actually not true. In fact, implementing programs is a very small part of the software development lifecycle. And what is this lifecycle? It's basically the overall sequence of steps needed to complete a large-scale software project. Studies have actually shown that on big projects, I mean, we're talking about like huge system software things such as developing operating systems or compilers or even large applications for companies. The initial implementation of a program may occupy only about 10 to 20% of the total time that's actually spent by program designers. About 25 to 40% of the time is actually spent on the problem specification and the program design. So I mean, this area is the important steps that come before we actually implement, the planning. I mean, before you can actually start typing away and writing code, you got to spend some time planning on what must be completed or how to actually solve the problem. So a good chunk of time is actually spent during this planning process. And then another 40 to 65% is actually spent on what you do after you implement. So we're talking about reviewing the code, modifying it, fixing it, and even improving it for doing all sorts of stuff. And then there's still the documentation. Don't get me started with the documentation, but there is a lot of written documentation that actually explains what all these different parts of your program does. So I mean, we'll go over these steps in more detail a little bit, but I really want to make it clear that the implementation portion of the software development life cycle is only a very small fraction compared to everything you got to do before and after writing the code. Most beginning programming students probably aren't going to see or even appreciate the entire software development life cycle because most of their programming assignments are usually pretty small, maybe 50 to 100 lines of code at most. And these are really small, simple assignments. You might not think that they're small and simple when you're actually doing them, but a couple of years from now, if you look back, you're going to see, oh man, these were really simple projects. Why did I have so much trouble back then? But now some of your upper level classes, they may involve a couple hundred lines of code. So a little bit bigger than what you're used to, but still, compared to real world problems, these things that you're going to be doing in your classes are very small. Most of the real world programs that people are writing are thousands or even millions of lines of code because we're talking about truly large software systems. So I mean, it's going to be a big task to make sure that you are writing code properly, you're writing it correctly, and make sure you're doing all the necessary steps. Because if something is wrong and you have to go back and look over your code, well, if you have to go back and look over millions of lines of code, you're probably not going to have a good time. So you're probably asking, what exactly is software engineering then? Well, it's concerned with the development of large software projects, not writing these very small programs that you're going to be doing in your introductory programming classes, but dealing with large-scale programming type projects. And with software engineering, as we mentioned before, a small fraction of it is just writing the program. You can't just write the program alone and say, okay, I'm done, that's it. There's a lot of stuff that goes on before and during and after writing the code that is part of the whole software engineering process. And this usually is not an individual project. I mean, it's so large that you're not going to be able to do it by yourself. There's just no way. I mean, this is going to require group effort. It's going to require collaboration. It's going to require management. It's going to require organization. So you might want to start getting this idea of working with people in order to accomplish these tasks. In fact, for most of your classes that involve these large type projects, I wouldn't be surprised if you were put into a team to complete the project because it's just too overwhelming to have one person do it by yourself. Now, there is a formal process for developing this software, and this is what we call the software development cycle, and we're going to go over this in more depth. We'll now take a look at all the steps in the software development life cycle, and each step has its own purpose and activities. Each step should also result in a written document that reflects the past decisions and guides the future actions. So just keep in mind that every major software project is normally developed as a team. So these documents will help keep all the members of the team informed and make sure everyone is working towards the goal. Now we can break up the steps into 3 parts: before implementation, during the implementation process, and after implementation. So before we even start implementing any code, we need to do a feasibility study. We then would have the problem specification, and then the program design, and then the algorithm selection or the development of the algorithm, and the analysis of the algorithm. So just making sure all that's working. And then during the implementation part itself would be the coding and the debugging. And then once we're done with the implementation, we would then need to test and verify that it's working, and we would introduce some benchmarking, and then we would have the documentation, and then finally the maintenance. So we're going to take a look at each of these steps in more detail. The feasibility study will evaluate a proposed project and compare the costs and benefits of the various solutions. So the whole point here is that we need to consider all the costs, including any equipment costs and any personnel costs. So like for example, one solution might be to buy a new computer system for the project. Now, I mean, the cost of hardware has dropped, but it's still a significant purchase. And then we might have to also consider the fact there could be costs on top of that, such as purchasing laser printers or purchasing telecommunication links. And then we have to consider the cost of the software that's associated with it, maybe equipment maintenance, salary for developers or consultants, salaries for technical support people, data entry clerks. So all these costs need to be factored in. I mean, the overall cost of using a computer to solve a problem can be much higher than we actually expect, and it can be more than the value of the information that's produced. I mean, there could be other options that we have to consider as well. So, I mean, what we're doing is we're asking ourselves, what are the relative costs and benefits for each of the following solutions that we would propose? So we might propose things like buying a new computer, or writing new software for an existing system, or using cloud computing, or outsourcing to a contractor, or revising the manual for something, or cutting back the scope of the project. So we're just keep looking at the costs and the benefits of each possible solution. You don't have to worry about the nitty-gritty details of the solutions just yet. You're just thinking about how much is this going to cost us and what do we gain from it. Then you can actually determine whether it's a good option to pursue or not. So at the end of the feasibility study, there should be a feasibility document that expresses the resulting recommendations. So the creation of this document can be a very complex process that involves considerations that are that are similar to what we would see in business or in law or management, economics, and so forth. I mean, the purpose of the feasibility study is to make all project stakeholders aware of the costs, the risks, and the benefits of various development paths as a guide for deciding on which approach we're going to use. If we determine that the project is feasible and would benefit from a computer solution and that the software development is to go forward, then we can move to the next phase, which is the problem specification phase. So this involves developing a clear, concise, and unambiguous statement of the exact problem the software is to solve. And I mean, the original problem statement is most likely in the feasibility study, but in there it may be unclear, it may be incomplete, or even maybe contradictory. So, I mean, the idea is that we need to rewrite what is in the feasibility study to make sure that it is more clear, it is more concise. So, I mean, during this process, the software developers and the customers, the ones who are actually going to be paying for this and actually going to end up using it, would need to resolve each of the inconsistencies, each of the ambiguities, and all the gaps. It's a lot easier to make these changes at this phase in the process than to make the changes in the software later down in the road. So the result that we should get out of this is a problem specification document, and this would express the final and complete problem specification and guide the software developers in all subsequent decisions. So this document is going to describe exactly how a program behaves in all circumstances, not only in the majority of the cases, but even under the most unusual conditions. So it's going to include a description of the data expected to be the input to the program, as well as what results should be computed and how these results are to be displayed as output. It may even include limitations on the time allowed to produce those computations, or even the amount of memory that the program would require.